Statics, but not the kind where you shock people. By Mohamed, Colton, Erik, and Trinity. Next slide. So we start out with a relatable situation. It's October 1st and you decide you want to hang up your Halloween decorations. So you grab a box from the attic and you open it up. Except you see that the only decoration you have is a single fake spider. You look at your front porch and you see that the only place you can put the spider is between two hooks across from each other on opposite walls. Through the hooks is a rope that causes a roughly 30-degree angle of elevation on one side, and on the other provides proportions akin to a 3-4-5-sided right triangle. Also, the spider is 80 kilograms for some odd reason. You are unsure of how much tension the rope can support with its awkward configuration. Happens to everyone, right? So what's the problem? Next slide.
So that situation is similar to the problem that we are going to solve today, which is question 2 of the statics problem, which states to determine what the tension in lines B and A and lines B and C in newtons should be if they must support the weight of the 80-kilogram cylinder in the figure, similar to the previous situation. Next slide. So our knowns is that the weight of D is 80 kilograms. A horizontal angle of lines B and C is 30 degrees, and A and B has a hypotenuse of a 3-4-5 triangle. And the unknowns is the tension of lines B and A, the tensions of lines B and C, and the horizontal angle of B and A. And there are some assumptions that we need to consider as well, which is that there's no friction and it's in a vacuum space, and that the weight is about 784 newtons. And lines B and C is a hypotenuse of a 30-60-90 triangle. Next slide.
Since we're dealing with forces, our first step is to draw a free body diagram. That way we can easily see all the information in front of us. From this, we can see that lines BA and BC can be broken down into simple right triangles. So we can apply any trig that we need to. Through this, the 3-4-5 triangle template tells us that the horizontal angle of BA is 36.87 degrees, what we're referring to as theta 1. After drawing the free body diagram and seeing what's in front of us, we can begin to work towards calculating the tensions of BA and BC. Next slide.
So to break it down, we need to have all the forces be equal to each other, meaning that the horizontal forces at both ends need to be equal to 0, which means BCX and BAX are both going to be equal to 0, which will break down the tension X. And then we also know that the two vertical forces holding up need to be equal to the weight. So that then we know that the vertical forces of BC and BA added together need to be equal to what the weight equals, which is 784 newtons. Then using trig identities, we know that tangent of theta 1 is going to equal the vertical force over the horizontal force of BA, and then the same will apply to theta 2 for BC, which means that tangent 36.87 plus tangent of 30 degrees, both times a tension X are going to equal 784 newtons. And then using algebraic manipulation, we can add the two tangent of the angles together, which will equal 1.327 roughly. And then we can divide 784 by that number, which will get us 590.65 newtons, which is going to equal to our tension X. And then going further, we can use cosine identity to solve for the missing variable that we do need. And using manipulation, we can do cos the theta 1 times BA equals tension X, and then we do the same for cos 30 degrees times BC equals tension X. And then going further with the manipulation, we get 590.65 divided by cos of theta 1, and then the same for BC, it's going to be 590.65 divided by the cos of theta 2, which gets us for tension of BA is going to be 738.31 newtons. and the tension of BC is going to be 682.02 newtons. Next slide.
Verifying and testing. Answer does not consider some factors. We do not include friction and assume that our problem takes place in a vacuum space. This changes our solution slightly, not allowing for 100% accuracy. From a logical standpoint, our answer works. Having more tension on rope BA makes sense due to the object's displacement and rope angle, but still both ropes share the weight of the object, putting tension on rope BC as well. Furthermore, tension calculation has various uses and effects on engineers' decisions. From a hanging Halloween decoration to suspended bridge, tension is an essential factor to take into account. More specifically, hanging mass tension calculated in our question is used to measure the total amount of weight that a suspended object can be or hold. Here are some examples. This first example is a bridge tension analysis. If we allow for stress analysis and we increase the weight on the bridge, we could see that the tension of the ropes increase. So this is something that engineers will have to calculate to ensure these ropes don't snap or anything bad like that happens, and ensure the safety of those passing through the bridge. The second example I'd like to show you is something we're a little bit more familiar with. So if we increase or decrease the displacement to the left or the right, we could see a change in tension of T1 or T2. So the more we have it to the right, the higher the tension is over here. The more we have it to the left, the higher the tension is to the left. And if we increase the weight, the tension will increase for both of them. Thank you for listening to our presentation, and are there any questions?